Alright, now I'm in my IntelliJ. I have compiled a simple program to demonstrate how the theory really comes into practice. I have implemented a simple program to imitate exactly what we just went through. So see here, this is my main program. I have created an object called vertex. So where do I define vertex? It's here. This is my vertex class. It has one color. This color is an enum, which has only 3 fields: white, gray, and black. The map to undiscovered, discovered, and finished states. It also has a parent, which we saw in the graph. Every single node has at least one parent. And in the produced depth first forest, every single node has always one parent. So we'll use this parent to indicate this vertex parent. Then we use 2 integers. One is discovered timestamp, that's the initial timestamp when this vertex has been discovered in this traversal, and the second timestamp is finished timestamp. And there's one more field called val, which is just standing for the value of this vertex. Back to the graph, that means A, B, C, D, E, F. This is one constructor. This is a toString. I'm using this to print out this entire algorithm before and after we call depth first search, just to show how that really looks like. All right, now back to this main program. I'm using a tree map to hold all of the connections, the edges from one point to another, one vertex to another. Again, this is an adjacency list representation. I'm instantiating all of these 6 vertices here using Java code, and then I put all of them into this graph. This is a tree map, and the reason I'm using a tree map is because tree map can help you keep the entries sorted in order. And I'm implementing a customized comparator. I'm using the val as the comparison key so that all of the entries in this graph, in this tree map, will be sorted by alphabetical order, A, B, C, D, E, F, just for easy tracking. Then here, I'm printing out all of these vertex before I call the depth first search algorithm. So here I have a class called depth first search algorithm. This is the constructor, and this is the algorithm. Back to the main program, then I'll call depth first search, right? Or just call this. And then after we call this, I print out every single vertex again. The juicy part of this entire program is the depth first search algorithm. Now let's take a look how I mapped the theory into practice. How can we do that? I created the 2 fields. One is called time, which starts at 0. I have another field in this class called graph, which is a map. So when we instantiate such an object of DFS algorithm, inject this graph into this field. We have one main method in this static class, which is just called DFS. In the very first, what we do is that we initialize every single vertex in this graph to be white. That should be the initial state of every vertex before we start DFS algorithm, and the parent should be null for every single node. After that, we'll create a tree set. Again, for easy tracking, I'm using a tree set instead of a regular hash set because I'd like to everything sorted in alphabetical order just for easy tracking. For the depth first search algorithm, we need to go through every single vertex. If you recall, back in the graph, we have to visit every single vertex. Initially, every single one of the vertices is in white color. That means none of them has ever been discovered yet. The reason we need to put them into a set to go through is that just in case the end result of this depth first search is a forest, meaning there are disconnected vertices. If we don't put them into a set, we might miss them. And then this is the main part of this entire algorithm. So for all of these vertices, if the color of the vertex is white, then we'll just DFS visit. This is the recursive algorithm that we use to go through every single vertex. Now let's go here. What is DFS? This is a very simple recursive program. You see, these 2 are highlighted together. That means this one is calling itself. Let's see. The first time when we enter this DFS, we increment timestamp by 1. So we assign this 1 to this vertex discovered time. And then we color this vertex to be gray. Recall the graph that we just saw. For every new vertex, if it's white, we'll color it to be gray and assign a discovered timestamp to it. What's after that is we'll go through every single adjacency list connected with this vertex. So we'll get this vertex's adjacency list from this graph tree map. And then from this tree map, we'll just traverse through. Again, this is where the recursion comes into play. We'll check if the color, see here, if the color is white. If that is white, it's similar to here. If the color is white, what are we going to do? we'll call this recursive function dfs visit. So see here, we visit this v. What is this v? This v is every single vertex in this adjacency list of this vertex. And before we do that, we assign this vertex to be the parent of this one, which makes total sense. The reason we got to v is because we have access to vertex. All right. Then this function will come into here again. At that time, if time is 1, and then at this moment time is going to be incremented, time becomes 2, then the discovery time is going to be 2. Then we color the b node to be gray. We continue this. Then in the end, we have visited d, right? So what are we going to do? That's the end. There's nothing else that is white that is connected to 4. So then we're just finished. So at this point, we'll color this vertex to be black. That's what happened here. We color d to be black. And then we increment timestamp and assign the incremented timestamp to be the finish time of this vertex. That's why we have incremented time here and assign this time to be the finish timestamp of this vertex. Then we'll continue to do this for e. Now e is incremented and assign 6 to be the finish timestamp of e. And then timestamp is incremented again. We assign 7 to be b's finish time. And again, we continue to do this. We increment time to be 8. Then assign 8 to be 1 and mark A as black. We have finished traversing everything that is connected with A, directly connected with A. At this point, what are we going to do? We'll continue. At this point, we're back here. So we'll continue A, B. So B is visited. So B is not of color white. We're not going to enter this recursive function. Next one is C. So C is white. That means we'll call this function. So we'll enter C. So we'll continue to go through this, which marks C is going to be marked as gray, increment 1, and then go to F, increment 1. That's the end, 11, 12. Then we're finished. So back to here, if this vertex is C, that means we have finished traversing C. Then what's left is D, E, and F. All of these 3 nodes, they are black. So none of them will go into this recursive function. That means we have finished traversing this entire graph. I hope that makes sense to you. Now we can just quickly run this program and then you'll see what that really means. I'll just comment out this. Now let's run this program. So first, I'm just printing out everything, what each vertex is looking like. So see here, every color, every vertex is completely empty. It only has this val, which is A, B, C, D, E, F. I'm using a tree set so that it's in sorted order, so that it can be easier to track, right? And this A is mapping to here. A is connected to these 1, B, and D, right? A is mapped to B and D. That's what this arrow means. A is connected to B and D. And this one, B is connected to E. So see, B is connected to E. That's what this means. Now let me uncomment this. Now let's run it. Run. All right, so starting DFS finished. Now you see all of the colors of the 6 vertices are in black. Only 2 of the vertices parents are null, which is A and C, right? Makes sense? A and C. A and C, right? These are the only 2 nodes who don't have a parent because they are the root of their respective depth first trees. The second node, it does have a parent. What's its parent? The parent is A. Then what's this node? This node is B. So discovery time is 2 and 7 for B. B is 2 and 7. Exactly matches. Okay, now let's see. The third vertex is C. C, discovery and finish time is 9 and 12. 9 and 12 is here. Makes sense. The fourth vertex is, let's see, its parent is what? Is D. No, the parent is not D, but the value of this vertex is D. Value of the vertex is D. Discovery and finish time is 4 and 5. Is 4 and 5. I hope that makes sense. And E. E, this is one of D's parents, right? So E is here. Another parent of D is B, right? It's also here. B is also here. B. And also another parent. So D has 3 parents. Another parent of D is A. A is here. Discovery and finish time is 1 and 8. 1 and 8 is here. All right, let's go through the 5th vertex. The 5th vertex is E. E is here. E, 3 and 6. 3 and 6. And the last vertex is this one, F. F is here, 10 and 11, 10 and 11, and its only parent is C. C is here. parentheses here. That's the code. Now let's talk about this time complexity. O of v plus e, number of vertices plus the number of edges. Why is that? Because you see here, for all of the vertices, this one, the number of vertices is v, right? So we go through the number of vertices only once. If it's not white, we just don't go through, we ignore. And for here, this is going through every single edge for all of the edges. Only if the next vertices color is white, we'll enter this recursive call. If that's not the case, we'll just ignore. So we will not revisit any vertex or any edges. We only backtrack once. That's the beauty of depth first search and why the time complexity is big O of v plus e. That's the real code walkthrough. I have this piece of code published on my GitHub. I'll put a link at the description of this video. Feel free to check it out and play around with it. That's it for today's video. I hope this is going to be helpful for you to understand depth first search because it involves recursion and it's a very useful and practical, helpful graph search algorithm. It's going to show up quite often in an interview or just helps you understand computer science basics. Very helpful. If that's the case, do me a favor and hit the like button. That's going to help a lot with the YouTube algorithm and I really appreciate it. And don't forget to subscribe to my channel. We'll continue to go through more interesting algorithm and data structure so you don't want to miss out a new video. That's it for today's video. I'll see you guys in the next one.